Hello and welcome back to the last submodule within the Verilog1 notes where I illustrate some more principles of design using Verilog, using some examples. First of all, I promised you in the timing notes we'd come back to the comparator at this point. Remember, what we're trying to design here is a comparator that can give you the largest of four inputs, A, B, C, and D, and put that result into a register. And the most straightforward way to design it and the most straightforward way to code it is shown here. That is to do the comparison sequentially and put the largest number into the register G. And the coding for this is at the bottom here. Since E and F are the outputs of combinational logic, they have to go into a procedural block that's not triggered by POS-edge clock. So here I've used a verilog95 format, always at a list of the inputs, A or B or C. Begin, if A is greater than B, then that's the result. If C is greater than E, if that's the result. And I have the else's there in the opposite situation. In Verilog 2001, I could replace always at A or B or C with always at star. I then combine the last comparator and the G register into its own POS-edge clock triggered statement. G is a register, so I want it to be assigned after an always at POS-edge clock. If D is greater than F, then G is equal to D, else G is equal to F. We haven't gone through this less than or equal to type of assignment. That is called non-blocking assignment, which we'll get to in the next set of notes. And I encourage you to use it with registers, which is why I've used it throughout these Verilog1 notes when I'm assigning to flip-flops. Now I might ask you, why not move E and F assignments down to below in the always at POS-edge clock? And the reason is that now if we did that, E and F would become outputs of flip-flops. That is, we'd be inserting a flip-flop here and inserting a flip-flop there, or a set of flip-flops, the register. And we don't want that. They'll completely change the timing of this design and actually give erroneous results. Now we'll point out something here. This is the most straightforward way to code this particular problem. If I just asked you to do this and you're reasonably competent at Verilog design, this is most of what you would do if you didn't think about the structure of the logic before writing the code. You might recall in the timing notes I said there were better ways to structure the logic. In order for that to happen, you need to recognize that as a human and change the coding style to reflect the better structures of the logic. Let's look at those better structures. This was one better structure, that is to do the comparisons to produce E and F in parallel, exploiting the natural parallelism of combinational logic, and then do a second comparison to produce the output result G. For the same amount of hardware, this operates about 30% faster. You don't have to use continuous assignment, but here I'm going to illustrate this example with continuous assignment. So I've built the top two comparators using continuous assignment. You might recall the way this question mark colon aspect works is if what's before the question mark is true, we select the first selection, otherwise the second. So in this case, if A is greater than B, we will select A, else we'll select B. The second one here, if C is greater than D, we'll select C, otherwise we'll select D and assign that to F. Again, I could have used procedural code here, not a POS-edge clock block, but a always at star, for example, to do this like on the previous page. But this is different code than the one on the previous page. Here I'm very explicitly making these operate parallel rather than in a serial fashion. The second procedural block, the one that builds the register G, stays the same. This is the other improved coding structure that I had in the timing notes. We might recall here we've pipelined the results. We do one stage of the comparison every clock cycle in the pipeline. When the pipeline is filled, we're doing 3 sets of comparisons at the same time. We need these additional registers C1, D1 and D2 to keep the waves of data coherent. So we're always working on the same problem as the wave of data proceeds through the micro pipeline. You might recall a principle of RTL is that the outputs of all flip-flops have to be named because we have to assign them in a POS-edge clock block. So I've named these pipeline registers C1, D1 and D2. Here is the code for that structure. And in this case, and we'll see this when we get to the verilog2 notes, I actually need this this less than or equal to type of assignment, which I'll call non-blocking assignment, but we'll get back to that later. So here is the structure of that code. The first comparator in the top left, output E, assigned after a POS-edge clock, so E is the output of a register. The pipeline registers C1 and D1, second comparator writing into F, pipeline register D2, the third comparator writing into G. So this is the pipeline version. Again, this is very different code than the code 2 pages ago. The human has to recognize the improved structure, and the code then translates that improved structure into RTL. The synthesis tools cannot give you either of these improved structures on their own. The human has to recognize them. Finally, let's finish off with a simple example. We're going to design an 8-bit adder accumulator with certain properties. When accumulator is high, we want to add to the input in 1 and store the result in a output register called accum_out. Going to use absolute, not 2's complement numbers. When clear, just to simplify the overflow, when clear is high, we want to clear the contents of the register. I want to produce an overflow flag when adder overflows. I am not requiring here that we preserve the overflow flag for clock cycles after the adder overflows. To do that would add another flip-flop to the design. You'll need this coding structure shown down the bottom here. I remind you that physically an 8-bit adder produces a 9-bit result, the 9th bit being the carry out. This is how to code that in Verilog while giving that carry out a different name than the sum. What this structure on the left is called is concatenation in the curly brackets. We're concatenating the 8-bit variable sum with a 1-bit variable carry out, making carry out the most significant bit, which it should be to capture the carry out of this adder. We're going to use this in order to do our example. In fact, you might want to pause this video and actually do this example. Remember, design before coding. Sketch the design before writing the code. Okay, you've done that. Let's see if it's similar to what I produced. So we're going to sketch the design. I just got a head start here with some of the inputs. Remember, the first step, and a very important one, is to determine and name all the registers. What needs to be registered here? What has to be preserved from clock cycle to clock cycle? Well, the only thing that has to be preserved is the accum_out. I did not specify that overflow has to be preserved, so we do not need to put that into a register. So we're going to have a register, and we have to give it a name. We're going to give it a name, accum_out. The next step is to determine the combinational logic. A general way to approach this is to recognize that many of your registers will have alternatives as to what they're going to be on the next clock cycle. When you have alternatives, think multiplexer. So we're going to put a multiplexer in front of a register accum_out to determine what's going to happen, what's going to be put in there the next clock cycle. What are the alternatives that are going to go in? Well, these are those alternatives. Remember, if clear is high, we want to clear it, so 0 is one of them. if accumulate is high, we want to add in to accum out. I'm going to call that accum in because I need to name it for reasons you'll see in a moment. And if accum out, and if both of these are low, I just want to preserve accum out and cycle that back through the register. Again, I can be a little fuzzy in this combinational logic. Notice I've got 3 inputs to this mux and 2 control lines. It's underspecified. In fact, if this was built as a mux in the end, optimization might optimize that out. But if this was built as a mux in the end, several of these 3 inputs would be repeated. I'm going to grab my overflow flag from the carry out of the adder. That's why I have to name this, because I want to name that. Again, I did not require to preserve that, so I don't need a flip-flop here in this particular example. Finally, I do suggest that you hand generate a timing diagram to verify a design before going and coding it and debugging it that way. This might help you identify some problems up front before you spend a lot of effort coding and debugging. I've chosen not to present that in this case. I'll leave that as an exercise to the student. So finally, I'm going to code the Verilog. Remember, what I'm really doing here is translating the code into Verilog. My flip-flops have to be assigned in always that POS clock block. My mux becomes an if-else statement. So always at POS clock, if clear is high, that has priority here. Accum out becomes equal to 0. Else if accumulate is high, accum out becomes equal to accum in. Down here I build my adder. I'm using that concatenation, renaming the carry out overflow. So if this 9-bit vector on the left is assigned to the output of these 2 8-bit adds, which of course produces 9 bits, accum out plus in 1 becomes equal to the sum is going to be called accum in, the carry out is going to be called overflow. This was an unsigned example, so the overflow is simply the carry out. That is, if I produce a carry out, I know I've overflown my range using unsigned arithmetic. This is why I named accum in the previous page, because I have to name overflow. If I didn't need to have to aim overflow, I could just put accum in equals accum out plus in 1 up here. I then declare my local variables. Remember, this just depends on how the variables are assigned. Accum out is assigned in a procedural block, so it's a type reg. Accum in and overflow are assigned continuously, so they're type wire. Then have my module header, declare my inputs and outputs. I've used the verilog95 style here, and have end module. That reaches the end of these particular examples and the Verilog1 notes. What this has been is a complete pass-through of how to use Verilog to capture synthesizable intent from a drawing of the design, how to use a different subset of Verilog to exercise the design through a test fixture, and how to manage the synthesis tools to manage the other aspects of your design besides the logic, most specifically the timing and other aspects of synthesis, particularly design compiler, that are important for you to know. That puts everything together in one complete flow. What we're going to do now is go down into the RTL subset of Verilog in much more detail in the Verilog 2 notes. I look forward to you joining me then. Thank you very much.